Interrupted by physics today because there was no physics lab this week. Woohoo! I was told by the other faculty I was far too happy about this, but I stand by my elation. I stand by it. Let's begin with the prayer. Dearly Father, we thank you for this afternoon and for the weekend about to start. Just pray that you just guide our thoughts, help us to just start to understand something about quotient spaces and a little bit more about topological groups. Lord, in your name I pray. Amen. So last time I introduced you guys to the concept of a topological group, and a topological group is kind of just what it sounds like. It's a topological space which also has a group structure, and it's assumed that the group structure is continuous. All right, so you have continuous multiplication, as understood from the product topology on the group across itself, and you have a continuous inversion. And topological groups are there's once you have a group, there's so much contained in that. I think it has to be connected, for example. Well, maybe, I don't know if that's true. You get these left multiplication maps which go from any point to any other point. I guess that doesn't, well, that's a question. Is a topological group connected?
They have proofs that some of them are.
What's that?
They have proofs that some of them are.
Oh, good. Well, let's find out which ones. We need not stay in doubt. Now we have already shown that if you take any 2 points, right? If you take any 2 points in a topological group, there is in fact a homeomorphism from one point to another. That was we figured the proof of that one out last time. And this is lemma. Well, let me just example. There's a couple examples, then I'll get to lemma. The examples are important. One, he mentions if you take G and give it discrete topology. So let G be any group, okay? Any group with the discrete topology becomes a topological group. Okay. See, that to me, maybe a topological group isn't too strong a structure. Well, I don't know. I mean So every group is a topological group then, in that term, in view of that. But maybe, well, when I think of a topological group, I don't think of the discrete topology. I guess I was born and raised in terms of Euclidean topologies and such, so the idea that the discrete topology actually is a legitimate topology kind of rubs me the wrong way. I mean, definitions are definitions. It's legit. I mean, that's done. We don't get to unchange the definition of topology, right? But certainly you're entitled to your opinion about which topologies seem more natural to you than others, right? And I do think it's fair to say some topologies seem more geometrically reasonable than others. That's really not useful language in mathematics, these kinds of judgments, right? Well, are they? I don't know. I debate these things. Additive groups. If you take Rn paired with addition, or if you take Cn paired with addition, so additive group under addition, right? These are topological groups in the Euclidean topology. So, topological group. And I would assume, well, I mean, obviously, you could also make them topological groups with respect to the discrete topology, as we have spent too much time talking about already. All right, something a little bit more interesting. 3, and I may have talked about this already, I'll talk about it again. If you look at GL and R, let me just remind you what this is. This is the set of invertible n by n real matrices, all right? And so basically the fine print here is we look at n by n matrices and we isometrically embed them in our n squared in the sense that there's a mapping like psi, right? And I don't know which way, chicken or egg, but the length of the n squared vector is the length of the matrix over here and vice versa. So that's what I mean like an isometric. It preserves that notion of length of vector. Right? I mean, essentially by definition, you're kind of really building the vector length over here using that bijection, which is just the natural thing of stringing out the elements in the matrix. I mean, I guess this over here would be the Frobenius norm, if you want to build it from a norm. Okay, so this is open in Rn squared in the sense that you make this identification. But this actually is the inverse image, and I think I talked about this already, but this is the inverse image of what? Well, it's the inverse image of the reals with that removed, right? But a singleton is closed, and the complement of a closed set is open. So that's the inverse image. It's the inverse image of an open set. GLNR is the inverse image of an open set. Hence, GLNR is open in Rn squared. Okay. And of course, it's a group. And by the way, matrix multiplication and matrix inversion, those are continuous. Because matrix inversion, you can look at the classical adjoint formula, for example. And what that is it's a rational function in the entries of the matrix where you don't have division by zero. That's clearly continuous. And matrix multiplication, well, that's a linear combination of products of the entries of the things, and that's also a continuous function. Again, like I told you guys, kind of the philosophy here is if you have a formula, it's probably continuous. I have to work kind of hard to give you a formula which fails to produce a continuous map. All right? They exist. People make their careers on that kind of nonsense, don't they? I guess you guys wouldn't have experienced that yet. But. All right. Here's the lemma. Lemma 4.57. Let G be a topological group with neutral element E, then G is Hausdorff. G Hausdorff. All right. If and only if. What? What? Oh. I see the import of this lemma. Just a second here. I got it. G topological group. Now, is that a characterization we had before?
Is what a characterization?
Did we have before the theorem? No, I don't think we ever had a theorem that stated that it was Hausdorff if and only if points were closed. That's not a theorem we had. What we did have was the theorem that if the topological space is Hausdorff, that implies that singletons are closed sets. That we did prove. Okay? So, in particular, the singleton just containing the identity element is closed. Yeah. So that direction of the proof is clear, right? So this direction, well, Hausdorff implies that G closed for all G in G. So in particular, G equals to E goes, right? Where you use the identity element. How about the other direction here? So we do what? Assume. I'm going to jump off the deep end and just try to freeform prove it, see what happens. There's no telling. Assume the singleton E is closed, right? We want to show G is Hausdorff. So what do? E is closed. What's that mean? That means that G with E removed, right, is open, right? So I'm trying to just picture it. You got this topological group G, right? You take two points, X and Y distinct, right? Our goal is to separate those. E is somewhere. Say here, whatever. Then your goal is to find open sets which and I know I've got these homeomorphisms that map E to Y and X to Y. I mean, I've got homeomorphisms between these points given by the left multiplication, right multiplication maps. Seems hopeful. How do you do it? Okay, fine. That's what we spent tens of dollars on this book. I'm impatient. I'll use the book. It's so few sentences. I'm going to feel silly once I read this proof. Ooh, maybe not.
It's not that obvious, but it just uses the diagonal. So.
Oh, it uses the diagonal? I would never have thought of it then. I'm quite a ways. I'm way down here at the level of, like, I'm down here at the level of, like, Math 200 proofs, right, or typical linear algebra problem. I mean, most of your linear algebra problems, it's very little more than using the definition, right?
Pretty true, yeah.
I don't even really use the machinery that much yet.
I mean, I think it's fair considering most of them actually haven't had 200 too, like you keep saying.
That needs to change.
Yeah.
All right. So we consider the map. What do? We have to use continuity of the map, of the product map. So phi is the multiplication, I assume. Yeah. So phi of GH is equal to GH. Oh no, it's not that. It's the combo map. It's got the inversion and the multiplication all up in one, all wrapped into one. By the way, it suffices incidentally to know that it's a group and to know that this mapping is continuous. From that automatically follows the continuity of the inverse map and the multiplication map. So for those of you who are like definition purists, you would be like, my definition of Lie group is wrong, because I could just say it's a topological group such that that map is continuous, and that would be equivalent. And then it would become a theorem that the product and the inverse were separately continuous. For pedagogical reasons, I don't do that. It's also why my definition of vector space is hopelessly clumsy. All right. All right, so what's next here? That's the composite, bless you, of continuous maps, and is hence continuous. I mean, that's fair enough. Here you've got, this is actually what, this would be like, phi is actually equal to M composed with the identity Cartesian product with the inverse map. The Cartesian product of continuous maps is continuous, and the composite of a continuous is continuous, so phi is phi is continuous. Where was I? Since phi of GH equals E, if and only if G equals H, so phi of GH equals to E, if and only if, what, G H inverse equals to E, which is only true if G is equal to H, fine. Those are reversible statements, of course. What does that mean? The pre-image of E is precisely the diagonal. inverse image of E is equal to the diagonal in G. Of G, I should say, not in G, right? Remember what that is? This is a set of G, GG. So G is in G. Then what?
Diagonal's closed. Since
But then, oh, but that proves the diagonals, so therefore, but this is continuous, that's closed, so therefore the diagonal is closed. Bless you. It's just out here. It's nothing to do with music. It's here.
Girl sneezed in the C lab the other day, and I didn't think, and I said, instead of saying bless you, I said excuse you. She gave me a really weird look, and I didn't realize it until afterward.
You should have told her you're so good looking. That would have been more awkward.
Probably.
Especially if she didn't watch Seinfeld. Let's see here. So the diagonal's closed, and so we proved before that diagonal is closed if and only if the space is what? Or is it if only if, or is it? Okay. So G. Hausdorff. All right. That's kind of a typical group theory result. You don't have to check an arbitrary point, all right? Like, what happens at the identity, you know? That seals the deal. So, that's not an unusual kind of thing. Excuse me, to see in group theory, to see in study of groups, topological groups or otherwise. All right, so what can we do with that? I guess we'll just put that on our list of things we know. Let's add to this list. Actually, let me just start a new list. Ew, what have I done? Ginny has almost agreed to let me, she's starting to agree to let me buy the chalkboard. I'm wearing her down. I keep asking for it every day. She's getting tired of hearing it. So eventually, I'm going to buy that chalkboard. But I don't know. Part of me doesn't want it. It's $300. I don't know. It's kind of a lot of money. If I played video games, it'd be like a system, right? I don't know. But I don't play video games, so like, chalkboard is my video game, right? So it makes it okay.
There you go. And you don't even have to buy the games for it.
That's right.
Cheap chalk.
Chalk are my games. That's right. And I don't want that dustless chalk. I want the dustiest chalk I can find. I want it to be soft and just, yeah. I'm afraid that dustless chalk will scratch my board, my precious board. Let's see here, GL and R. Then I'll invite the other mathematicians to my office to show them what a chalkboard looks like. Now, I'm not using his notation. And so he's got like MN, comma, NR, right? But this is my notation for that, which I'm going to stick with. So this is GLNR, SLN. So this is just going to be a laundry list of examples here.
What's SL again?
Special linear group, order n, equals to un. So the determinant of the special linear group is 1. SO and R. These are the special orthogonal group. This is a n by n real matrix such that A transpose, I usually write A transpose A, so whatever, they can deal. A transpose A is equal to I. You can put the transpose on either one, it doesn't matter. And the determinant of A is equal to 1. If you peel off that determinant 1 condition, that gets you back to ON. These are all capitals, by the way. These capital, 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 capital. Don't miss these capital S, okay? ON Same song and dance. Except it's not special. All right. Sorry to hurt its feelings, but it's just the way it is. Oh man, it doesn't even have it on this list. What?
It's 4 o'clock.
It doesn't even have ON on here. What?
But I guess it's not special, so
Oh, well.
it's not on the list, didn't make it.
But I like it. It's an example of a disconnected one. It has two connected components like I talked about the other day with you guys, right? Oh, okay. Well,
Does
whatever.
it GLN also have two connected components?
I don't know. Yeah.
Like, I thought
Oh.
we showed something similar to that in advanced
Oh,
college.
right. Yeah. Right, because you can either have positive or negative determinant, and you can't cross through zero because it's not in there. And then you can do the same as these, right? You can talk about GLN C. You can talk about SLN C. You can talk about SO. Oh, wait a minute. No, we don't talk about that. We talk about.
That's you.
We talk about SUNC. Well, he talks about UNC. Oh, UNC, I don't like that at all.
That's more special than ON.
UNC, that's just not a good thing to call anything. Sorry. I feel like if there was a UVA group, we wouldn't like that either. Sorry. No. Just a second. Fine. Oopsie. I'll do U. UNC. Ah, I hate to say that. This is U in n by n complex matrices such that U dagger U is equal to the identity. Here U dagger is U conjugate transpose. Now GLN is just A in Cn by n such that
Determinant is 0. Dividend 0.
yes. So much writing. Why am I writing this all out? I started. I can't stop. I'm sorry, guys. This is so boring. Sorry.
So U conjugate the matrix C, like there, it would just be every individual component of U with the complex conjugate.
Yeah,
With respect to every.
Hey, let's
single
look at an
component.
example. So like I, 2I, 1, 3, dagger. All right. So what that would be you can do either one first. Doesn't really matter. I'll do the conjugate first. It's already that way.
By.
Yeah, minus I, minus 2I, 1, 3.
One. You go two. Yeah. Okay.
Yeah, so there would be the.
Just making sure.
Yeah. Now, of course, that's not a unitary matrix. That's just an arbitrary 2x2 complex matrix I made up.
Yeah.
If a matrix is equal to its conjugate transpose, it's said to be a Hermitian matrix.
Okay.
It's the complex analog of symmetric. Likewise, if it's equal to minus its own dagger, it's said to be skew Hermitian. Okay, anyway, so this, if we talk about SUNC, this would be the special unitary matrices, order n. And so what that is, well, I like how he writes it. He's like, it's just UNC. Oh, I don't like that, actually. I have to say that again. Intersect with, what? Oh, right, I already have that. Yeah, thank you, SLNC. Very good. I was just about to write the definition of SLNC out, only to go, oh, duh. Okay, yes, so it's unitary matrices which are also determinant 1. Yeah. Man, you can build a lot of current physical theory with just these things. Direct product and tensor together and such. And the representation theory of these is, very, very interesting to current quantum mechanics. Right. Anyway, these are all subspaces, as he mentions, of either Rn squared or Cn squared. As he says, in particular, they are metrizable and so Hausdorff. All right. So if you can view them in terms of a metric topology, metric topologies are Hausdorff. We prove that. And oh, yeah, here's that thing Daniel was warning me was coming. Proposition 4.58 says that GL plus which kind of is what it sounds like. That's A in GLN such that what?
Determinants plus.
Right. Now that's that, and also GLNC is connected. Now, you could also talk about, just let me use a little color coding, save myself some writing. Minus would be the other way, right? And yeah, I think we talked about that before. So if you took the union of both of these, you get all of GLN R. And by the way, this is the inverse image of the open ray from 0 to infinity under the determinant map. So this is an open set. Likewise, the negative GLN is an open set. So what you have then is, of course, GLNR is, it's covered by the plus and the minus, both of which are open. That's a separation of the set. It's disconnected, right? Because there you go. That's a separation of it into positive and negative determinants. However, those different things are in fact the connected components like we talked about before. So this GL plus or minus is connected, and separately, either the plus or the minus, obviously. GLN C is connected. If you don't mind, I will try to read the proof out loud to you and see if it makes sense. He says, we shall only prove that GL and R is connected, for GL and C is completely analogous. So, he says the group GL1R coincides with the interval 0 to infinity and is connected. And then he says, proceed by induction. Suppose n is greater than 1 and that GL n minus 1 R is connected, positive. N minus 1 by n minus 1 matrices are connected. He says, consider the map P that goes from n by n matrices to Rn, sending a matrix to its first column vectors. If we isolate the first column from the others, we can write n by n matrices as Rn cross n by n minus 1 matrices. And then P is the projection under the first factor of the product. This makes P continuous and open, so its restriction to the open set GLN R subset of n by n matrices open. Moreover, the projection map maps you onto Rn with 0 removed. We claim that the fibers of this map are connected, and then from lemma 4.18 the connectedness of GLN R will follow. Wow. It's a very nice argument. It's using, remember that thing we had about if we have that the fibers are connected, then we get that the domain is, so where do you have that? I'm thinking of something else.
That sounds right.
So what do you say, lemma
F is open or closed in the whole.
4.18, lemma 4.18. Let Y be connected topological space, F from X to Y continuous onto map such that the fibers are connected for each Y. If F is open or closed, then X is connected. Ah. Right, okay. I'm thinking of another one that it sounded to me kind of like that, but it wasn't that one.
Yeah, I think we had a similar one for closed, like if the fibers of...
Oh yeah, the theorem 4.44, consider a closed map with Y compact, the codomain compact. If the inverse image of Y is compact for every Y, then X is compact. So there's kind of this theorem for both compact and connectedness. Like if you have the condition on the fibers, and if you have a closed map, or in the other case also open, then you get compactness or connectedness of the domain from the compactness or connectedness of the fibers, provided that it's a closed map, or in the connected case, closed or open by lemma 4.18. Wait a minute, no. Yeah. Sorry. It's, I was misreading it. Let's see here. All right, we should look at this. The idea of this construction is a useful technique. So we should like look at it a little bit more deeply. Oh man, I gotta erase all these. Why did I write them? Why did I even write these? What's wrong with me? I should have read those. It was useful to you, Jess, right? I'd say it was useful.
It was useful.
Thank you.
Hey, I learned the dagger.
I feel bad. Now, by the way, I should mention, although not really appropriate for this course, but for the other course, if you look at little GL NR, little SL NR, SO NR, little O NR, GLNC, SLNC, little U NC. I think you see where I'm going with this. SU NC. These are all the so basically what you have here is G. What you have over here is what's called frac G. And frac G is identified with the tangent space at the identity element of G. This is a Lie algebra. It induces this Lie algebra structure through the bracket of vector fields at the identity of the Lie group. In fact, these are all Lie groups because it's not just that these are continuous; they're in fact smooth. But that's for another day. So just saying.
Do we go over all those other kind of groups in linear? Or just a few of them, or do we go over more than just GL?
To go over any?
If I do these in linear algebra, I would be misbehaving.
Now I kind of want you to.
There's
I mean,
there was
You
homework
should do at least
once
something
on,
else with
like,
one of the
SON.
spaces.
It'd be what?
There was homework once that involved SON, I think.
Yeah, oh, I could put in the homework. That's true.
Yeah, we didn't cover it in class last year.
I mean, you started using the notation like GL. I mean,
Oh,
we-
I will.
it's
Yeah, I
just
will. Oh, I will use the notation. I just won't.
Yeah.
I won't make good on showing you that it's all just the same story all the way down. It's all just Lie algebra and Lie group. We use the capital letter for the Lie group. We use the lowercase letter for the Lie algebra. And that's the standard notation for it. And there's beautiful connections between the structure of the algebra and structure of the group. But again, I guess that's for Monday when we meet again. All right. So what was our claim? I guess we don't want to look at why is G L plus, right? And R connected. So the first thing is GL plus 1R is what? If you look at that, that's just A, right? And R, because 1 by 1 matrices just identify with R, such that the determinant of A is greater than 0. But the determinant of A in the 1 by 1 case,
That's just it.
yeah, this is exactly this. This is just this, and that's an interval, and that's connected by real analysis that I almost did in here. Not really though. Suppose inductively that GL plus N minus 1 R is connected, right? Then what he says, he's like, okay, so then we can look at GL. What's that?
N minus 1.
Oh,
Right.
yeah, N minus 1.
Oh, sorry.
I wrote it, but I didn't say it.
Right.
So GL, we can look at GLNR. We'd like to show this is connected, right? If we can show that, that's the induction step, and we're good to go. So, all right. So this is the thing we're basically struggling with. We're looking at something like a R by N by N matrix, right? And so what you can look at that. I mean, if something in here, let's say A is an element of that, right? Then that means A is something like A1, A2, AN, right? where those are each n vectors. So there's this like natural. You can think about it in terms of like a function of its column vectors or something like that. Now what he does, more specifically, is do what?
Pulls off the first one.
Yeah, consider the map sending the matrix to its first column vector. So he defines P, basically in terms of my notation, P of A is equal to what?
A1.
A1, right? So this P is a mapping from what? It's a mapping from, and let's see here, he takes the viewpoint that this is really an element of, how to say this? He looks at this as being something like Rn crossed with R, how many rows, and how many columns, n minus 1. So what he's doing is he's saying, well, this is really a Cartesian product of this and then all of those. Right? So you can look at it, and I suppose he could have developed a theory of projections for more than two factors too, he just hasn't bothered. So, I mean, left to my devices, I would probably say something like P is a mapping from the Cartesian product of Rn with itself n-fold times. To me, that's more natural, but whatever. So this is mapping as a P, is mapping from this Cartesian product, right? To its first, I mean, it's a projection onto the first component. Okay, so then what? He says this makes P continuous and open
From the product topology.
in the product topology. So P is continuous and open in the product topology. And then what? So you can this is what you can restrict it, right, to the open set. Now this is, notice I haven't said anything about, I've not said anything about GLN plus yet, right? So this is just a generic comment for just an arbitrary n by n matrix, right? This projection onto the first column is a continuous open map. Now, if we restrict P to GLN, right, plus NR, it's still continuous and open because restrictions are awesome. Let's see here. Where are we? And more than that, the projection. So if you look at the projection, what's the image? Okay, so what's the image? P of GLN. So here I'm saying restriction, here I'm saying image. What's the image of this guy?
It's going to be all reals except 0. The first column could be anything except just a 0 column.
Do you guys agree? Do you see why that is in terms of linear algebra, Jess?
Say it one more time, sorry.
He's saying that what we're doing, what this mapping is, right, is it's just taking the first column of an invertible matrix. So if you think about it, it could be absolutely everything, anything rather, except for one thing. It can't be 0, right? Because if a 0 is in there, that would make the columns of the matrix linearly dependent, which would violate various theorems we have in linear
And
algebra.
you know the determinant would equal 0.
Yeah.
So
Oh, very good.
violates.
Determinant 0. It's a good one to go to. So, in other words, anyway, Rn minus the with the origin removed, right? So then what? So what we have then is we've got P restricted. We can look at it. P is the mapping then from what to what? From GL plus NR to Rn with 0 removed. And then what? So then we're going to use that lemma 4.18 to try we can establish that, so P is open, okay, so the lemma applies, and we just need to show that the fibers, right, are connected. We haven't used the induction step yet, have we?
No, but we're about to.
Okay, I was gonna say, the induction step's gotta come up here somewhere. It's kind of funny. He looks at the inverse image of just E1. I mean, so if you think about what there is, if you want to understand inverse images, if you're right, you got different things to consider. I'm not. Why do you understand why he looks at E1?
No.
Is it just to look at something?
I think so.
I mean, our goal is to show that if this is whatever's in here, we need to show. Call something in here Z. So we need to show that P inverse of Z is connected for each Z. For each such Z, right? Then lemma 4.18 will then imply that this is connected because all the fibers of this open continuous map are connected. Which makes sense, right? That means, I mean, if it's an open continuous map, that means that the domain can be formed by basically gluing the fibers together. Right? It's a continuous map, they're adherent. And so if every one of those is connected and they're stuck together, surely the whole thing is connected. It intuitively makes a lot of sense, that lemma. I'm buying time. Okay, so how do we? Unfortunately, I don't have a parallel processor, so I'm really just wasting your time. P inverse of 1, 0, 0, 0. He looks at that for some reason. I'm not sure why. What is that? That is the product. I mean, okay, so that's what is that? It's this is very, very pretty. So you're looking at, right, the first column is E1. And then stuff over here, right? Some kind of, man, well, so it's 1, 0. But there could be stuff up here too, you know?
Yeah, we don't care about that.
We don't?
Well,
Oh, we don't. We don't! Why don't we care?
because by the
If I call this thing, what's M? What's the determinant of M?
this determinant of the
Yes, by the,
cofactor.
yeah, it's a block diagonal.
Right. No,
It's kind of a very ridiculous block diagonal matrix, but there's the, we just pulled out a kind of big gun to do that. Product of, determinant in terms of block diagonals, that's a non-trivial identity about determinants, but hey, we know it, so let's use it. With that, it becomes clear that B is what? See, because this M has to have determinant, like M is in here, so it has positive determinant. Consequently, the determinant B must be positive. Consequently, B is an element of what?
GL plus n minus 1.
Yeah. Okay.
I guess we do care about the first row, because that becomes the column that is taking the Cartesian product with.
Oh. Well.
I think this star row vector is that Rn minus 1.
Yeah. Oh, right. Right. Oh, yeah, that's, I mean, this is relevant. What we did is not wrong, but the thing is how to understand what this is a set of things, okay? What can we identify that set with? This set is in one-to-one correspondence with these guys and those guys. So that's, in other words, it's interchangeable with like a copy of Rn minus 1, which is, like you're saying, it's the cutoff first row, and then Cartesian product with this guy. Right? But both of these, well, you can easily prove that Rn minus 1 is path connected, hence connected. Right? And so we have a Cartesian product of connected sets. Connected. Inducted. Done. Okay. I'm not sure inducted is actually a word, but...
Well, yeah, that's just for E1.
Oh. Oh, man. Oh. Let me make me think again. She's like, given any y, the fiber is not empty. So let P of A equal to y. Left multiplication is a homomorphism from the relation PAB equals APB. It follows that. Okay, so then he proves next that the fibers are homeomorphic. And so if we've proved that this one is connected, all the other ones are also connected. Okay. So how would you prove? Well, I mean, the proof that they're homeomorphic involves basically matrix multiplication. I think his argument is clear, but I don't really want to write it out if that's okay with you guys. So, to finish it, you have to show that this other fiber there's a homeomorphism from this fiber to the E1 fiber. And since connectedness is a topological property, the fact that this and that are homeomorphic means that if we've shown that the E1 fiber is connected, then they're all connected. Consequently, by lemma 4.18, the whole thing is connected. Yeah. And I think I know exactly what he's saying, that the proof for GLNC is totally analogous. Right? Where did we use?
The fact that it's real.
Yeah, where is it that it's real makes it different? Is right up here. See? The determinant of A is greater than 0. In the one-dimensional complex case, this is GL1C. And so in GL1C you have, so if I was just to erase the plus, then I would have disconnected thing. I would have minus infinity to 0 and have 0 to infinity, right? Wouldn't be connected. But in the case of the complex, right, what happens in the one-dimensional case? Well,
Just a little different.
that's it. So that's just or as we sometimes call it, the multiplicative group of complex numbers. Non-zero complex numbers, the puncture plane. That's connected. So the same stupid inductive argument works. And so GLNC is connected. That would have made a really nice, man, if I ever teach topology, this will be a homework problem. Yeah. Sorry. Oh, I'm teaching topology now. What am I thinking about? I don't feel like I'm teaching topology. I feel like we are learning topology together.
That's why it's called independent study.
Ah, yes. On occasion, I teach something in here. Oh well. If I had more time. All right. Enough.
Basically, you're just saying that, like, the way you did that, like, the application for all the other like matrices was the same, kind of the same method as once we proved the line 0 to 1 on the real numbers is connected than it is for all things in the real line. You're saying it's very similar to that?
No, I was saying that this exact same argument that we made for the real matrix, how would it go for the complex matrix? You take an n by n.
Oh no, the one before that. Before that, same for all cases. Like you did it for just E. You did it just for 1. You won. Then
Oh,
say, what
He
about all
gives
the
the
other
argument in
matrices?
the book.
No, the argument to get the other fibers is that you have to show that the other fibers are homeomorphic to the E1 fiber. There's actually a homeomorphism, a one-to-one continuous map with continuous inverse from the inverse image of E1 to the inverse image of anything else. In terms of matrix multiplication, like Daniel was saying, it's on page 81, it's right.
Mhm.
Do you have your book? No.
It's not.
It's-
You don't have to do it. It's me.
Oh, okay, but it's page 81 right there. It's
But isn't that how we did the connectedness for the real line? Is because we could make it any other interval homeomorphic to 0, 1.
fair enough. Yeah, the fact that we have homeomorphisms between intervals is, I don't remember I'm not sure what you're reminding me of. I can't be sure. I mean, we definitely use this idea that homeomorphism transports connected sets to connected sets.
Yeah.
But
Okay.
all right, let me just kind of finish my thoughts here. The topological groups SLN and SLNR and SLNC are connected, and GLNR has 2 connected components. We mentioned that before. Let's see here. How does he get that SLN? How does he get that SLNR and SLNC? Oh. Not sure how he's gotten that SLNR and SLNC are connected. Because it's a corollary. Maybe it's okay. So, what about is a closed subset of a connected space connected? I don't think that has to be the case at all. No. So he claims that SLNR and SLNC are connected. This is corollary 4.59. While GLNR has 2 connected components. That we've talked about already. So what does he say? Ooh. Sneaky. Oh man, that's sneaky. That's sneaky. That's very sneaky. Check this out. Oh man, that's really slick. So what we want, right? You guys can think of this yourself once you realize that you can do it. You can do it. So what we want, right? We already know that GL and NR, right, plus is connected. We want a mapping, a continuous mapping from here, let's say F, to here, right? If I can get a continuous map, what do we know about the connected image of a continuous image of a connected set is connected. What's the map?
It's made by the determinant.
Yeah, exactly. So you take, but you got to be careful. You can't divide the whole thing.
Right.
So, because the determinant's multilinear,
Right.
so what we do is we say like f of a is equal to basically, I guess I need to use column notation again, but we just say column 1 of a. I mean, it doesn't really matter which one you pick, but column 1 will do. The determinant of a, which is non-zero, by the way, right? And then everything else. Proceed as usual, right? And you can calculate the determinant of f of a, right, is 1 over the determinant of a. Yeah, times the determinant of A. By multilinearity of the determinant, I can pull the constant out of the first column, and that gives me un. So there you have connectedness of SLN. That is slick. And the same thing will work for SLNC. Man, wow.
That's surprisingly nice.
That is. You know, I get the easier the argument is, and here the happier I get. So it's sad, but true. All right. He says, for the study of orthogonal and unitary groups, we need a preliminary result. He says, if you have a surjection, a continuous surjection from X to a compact Y, which is connected in Hausdorff, if all the fibers under F are connected, then X is connected. Okay, I guess I'll just, it's kind of a lot to hear. Let me just write it down. This is apparently like just an almost immediate thing of something we already did, right? This is a cancerous outgrowth of a lemma 4.18 or something. Oh, I'm sorry, it's unfortunate imagery. Let's see here. Let F from X to Y be onto continuous. And we're also assuming that Y is compact. What else are we assuming? Connected. Wow. Very greedy. Y is compact, it's connected.
I think X is compact.
Ah, yes. Alright.
And Y is Hausdorff.
Connected and Hausdorff, okay. Anything else? And then if the fiber over Y, if F inverse of Y is connected for all Y and Y, then X is connected. Again, he says the map F is closed, so clear it's closed. How do you know it's closed? It's a surjection. It's continuous. X is compact. Y is, there's so much data here. This is the map F is closed. Perhaps that follows from the connectedness of the fibers. No? Well.
Let's do the fact that X is compact. Otherwise, Hausdorff.
Oh.
I'm not sure if that's anything we should.
Oh, that's right. There was some kind of very surprising theorem back. You're right. I haven't found it yet, but I believe you. Oh, corollary 4.52, page 78. F continuous, X compact, Y Hausdorff, then F closed. Hey, couldn't he at least... That was like 4 whole pages ago. It's very rude of him not to say that.
It's supposed to be a fresh memory.
If only I had a photographic memory. Oh well. Or just some memory. Alright, anyway. Now we have that. After applying level 4.118. He has this proposition. And as much as I love topological groups, I want to go on. So, SONR